This video marks the beginning of complex integration as we continue with the complex numbers playlist. So, and we'll be talking about contours and paths. You know that a complex plane is a two-dimensional thing, right? So that's why it's possible to talk about contours and paths. So by way of definition, a path or curve is a vector valued function, r of t, which is a collection of x of t, comma y of t, or r of t is xt, yt, zt in the three-dimensional sense. The first one is in a two-dimensional sense, where t belongs to the closed interval a comma b, and that t is called the parameter. As t varies, the point traces a curve. We are talking about contours and paths, right? So paths in the complex plane is the next thing we like to talk about. So a path, or what you call a curve, is a function gamma on the closed set AB mapped to the complex plane. And it is written as gamma of t equals x of t plus I y of t, where x of t is the real part and y of t is the imaginary part. This represents a moving point tracing a curve in the complex plane. So then go ahead to talk about the types of paths. So we have smooth path, for instance. A path is smooth if the derivative of gamma, that's gamma prime of t, exists and it is continuous. So we say it is a smooth path. The same gamma of t we have here. So if we differentiate it and it exists and it is continuous everywhere, then we say we have a smooth path. Then we can also have a piecewise smooth path. So that's a path made up of multiple smooth segments. And then we can have a closed path. A path is closed if gamma of A is equal to gamma of B. Then we say it is a closed path. So, I mean, we're talking about this B now. This particular, this AB is the closed interval on which gamma is defined in the first place. So if gamma at A and gamma at B are the same, then we have a closed path. Then we go ahead to talk about contours. A contour is a piecewise smooth path used for integration. So path refers to the curve itself, and contour refers to the curve used in integrals. Okay. So path is the curve, and contour talks about the curve that we use for integration. And then we go ahead to parameterization, which is very useful in this sense. So to work with contours, we express them in parametric form. So, we said t is the parameter, right? So example one, if we have a line from 0 to 1, from 0 to I plus 1, then we can say that gamma of t is t plus it, right? So t plus it, and where t can take any value from 0 to 1. So in this case, for a unit circle, gamma of t is expressed as e raised power it, and t lies from 0 to 2 pi. So those are parameters we can use in that sense. So of course we know already that gamma of t is x of t plus iy of t. So, and the reason why we have this now would be that, this t now is, this is x. So it's like x is 1. So we just have 1 plus x plus iy of t. So I already, so it's I times 1. So y of t is also, is without with that t now. So because y is 1. So talking about complex line integrals, then we have this that given a function f of z, which is integral over gamma of f of z dz, then using parameterization, we have integral from a to b, f of gamma of t multiplied by gamma prime of t dt. Then the key, so if you use parameterization, we have this. Now, if you bring in parameter here, so for instead of gamma, we have a of b, and then we have t. T lies between a and b. So instead of f of z dz, we now have f of gamma of t, y prime of t, dt, like that. And the key idea here is that dz is y prime of t dt. So it's y prime of t dt, and then we can have all of this. So example one now, we have to evaluate the integral of z dz over over gamma, where gamma of t equals t plus it, and t is from 0 to 1. So first thing is to compute the derivative of this gamma of t, which is t plus it. So gamma prime of t, that's differential with respect to t, that's 1 plus I. Then the next thing is you substitute. So z now is z is now t into I plus 1. So that's what z is. And if that is the case, then the integral then becomes integral from 0 to 1 t into I plus t, t into 1 plus I into 1 plus I. And this is following this expression right here, f of y gamma of t, gamma prime of t dt. That's basically what that follows. So we have integral from 0 to 1 of t into 1 plus I dt. So if we tidy all of that up by simplification, so if you try to simplify this, it's like we have I plus 1 times I plus 1 is actually I plus 1 multiplied by I plus 1. So we have I plus 1 squared. And if you expand I plus 1 squared, right, you get 2I. That, in essence, this is what we are saying. You have I plus 1 squared, I plus, did I say I plus 1? 1 plus I squared. And that is 1 squared plus 2 into 1 into I plus I squared. And that is 1 plus 2I minus 1. So this cancels out. So we simply just have 2I. And that's how that came about. So this is 2I. So, and since it is 2I now, so we now have t multiplied by 2I. So we then have integral from 0 to 1 of 2it dt. So, and if we integrate 2I with respect to, of course, I is constant. So 2t, integrate 2t with respect to t, we have 2t squared. Or, I mean, I think I need to do that. The final answer is I, but let me just finish up that. Integral from 0 to 1 of 2it dt. Okay, so we have integral from 0 to 1 2it dt. So normally we can just say 2I integral from 0 to 1 t dt. Okay, t dt. And then that is 2I. When we integrate t, we get t squared, and that's from 0 to 1. So that is 2I. Uh, then evaluate now. So we have t squared, that's 1 squared minus 0 squared. Okay, this should be t squared over 2. Let me do that better. When you integrate t, you get t squared over 2 from 0 to 1. So that means you can bring out the half. So 2I dot 1 over 2 into t squared from 0 to 1. So that is then 2I. Okay, 2 cancels 2 already. So we have I multiplied by t squared. That's 1 squared minus 0 squared. So that means we have I into 1 minus 0. That is simply I. So that's what the answer is in that situation. So that goes. So the final answer is I when we evaluate integral of z dz over gamma, where gamma is given as t plus it in the parameterization. So talking about example 2 then, we have to evaluate integral of z squared dz along gamma, and gamma of t now is e raised by it. So this is talking about like a unit circle. So we have gamma of t equals e raised by it, and t is from 0 to 2 pi. So when we differentiate gamma prime of t, we get I e raised by I e raised by it, right? Because differentiate it with respect to t, you get differentiate e raised power it with respect to I, get I, then e raised power it remains. So it means z squared will be z squared would now be e raised power it. Z squared will be e raised power 2it. Okay, that's like the square of this now. So to now put it in the integral form, following it's the same formula we are still following. F of gamma of t multiplied by gamma prime of t dt. So now we have we have z squared now. We have e raised by 2it dot ie it dt. And when we integrate, we put all of this together. I is constant. We have e raised by 3it from 0 to 2 pi. And so Next, we have to integrate with respect to t. So the whole thing goes to zero. Okay, you may be wondering why. Let me just go ahead and do that. Um, so integral from 0 to 2 pi of 3 raised by it. Integral from 0 to 2 pi. Integral from 0 to 2 pi of e raised by 3 it dt. Right? Think that's it. Yes. So we have that, and that is equal to integrate this, right? We differentiate this with respect to t. That will give 3i. So that's like 1 all over 3i. Oh, okay, we had I out here before. So we have that I multiplied by 1 over 3i, into what we then erase that'll be erase power 3it. That remains, of course, from 0 to 2 pi. From 0 to 2 pi. So yeah, I think that works. Yes. So we have I cancels I already. So we have 1 over 3 into e raised power 3 I 2 pi minus e raised power 3 I 0, like this. So that's 1 over 3 into e raised power 6 pi 6 pi I minus e raised power 0. So that's like 1 over 3 e raised power 6 pi I minus 1. So e raised power 6 pi I is what we need to evaluate now. Um, so let me see if we can evaluate e raised power 6 pi I. Exponent 6 pi I, that should actually give us a result. Exponent 6 times pi times I. What does that give? So it actually gives 1. So exponent 6 pi I gives 1. So we have 1 over 3 into, that's 1 over 3 into 1 minus 1. And that is 1 over 3. 1 minus 1 is 0. So everything actually goes to 0. That's why the answer to that is actually 0. So we come back to the page. So that gives 0. Then we talk about path independence now. So if f of z is analytic, then the integral of f of z dz along gamma depends only on endpoints. So example, if you have integral from z dz, so the antiderivative, that is, if you integrate z, you get z squared over 2. And then if you then all of that then becomes end to start, do it over, like if you have a b, like the same way we've been substituting the endpoints the other time. So for path independence, if z f of z is analytic, then that would depend only on endpoints. So talking about orientation, then we have counterclockwise. Counterclockwise talks about positive orientation, while clockwise talks about negative orientation. So to reverse a path, we can say that integral of f of z dz along minus gamma is the same thing as minus integral of f of z dz along gamma. So this minus on the path here translates to the negative of the integral. Then we can also have piecewise contours. If a contour is split, and we say gamma is equal to gamma 1 plus gamma 2, then integral of f of z dz over gamma is equal to integral of f of z dz over gamma 1 plus integral of f of z dz over gamma 2. And then we can visualize that we can do a circle visualization, as you can see here. So we have this. Basically, you have the real part, the imaginary part, and then a circle is formed like that with a certain radius. So this is a circle of radius 1, actually. So here we have t from 0 to 2 pi, and then z is exponent of it, then you plot that. Then for a line path, you just have the line is now from 0 to 1, and then you have z is t plus it that we've had before, and then you have the line path this way. So in summary, we can say that a path is a parameterized curve in C, and then a contour is a piecewise smooth path. So and line integrals use the fact that use integral from A to B, you know, where t lies between somewhere from A to B, you have f of gamma of t, f of gamma of t, gamma prime of t dt. And the key skills we need here is to we need parameterization, differentiation, and substitution. And then important ideas include path independence for analytic functions and contour closed contour integrals often equal zero. So if you have a closed contour integral, it's zero. Then we have practice problems as usual. Let me see if I can show 10 at once. Okay, I think this will be too big for 10. So see, we have basic parameterization issues. You have parameterize the straight line from 0 to 2 plus I. So this would be like 2t plus it or something like that. Then parameterize the line segment from 1 plus I to 3 plus 2i. So I guess I suspect you have to subtract and then get whatever, like 3 minus 1, 2, 2i minus I, that is 2 plus I. So that you don't have 2t, maybe like the same line with this one. So these are the practice problems. And as usual, I'm going to solve. So you have first five basic parameterization. Second, you then have 5 to 8. That's computing line integrals. And you have circular contours, from 9 to 12. And then you have 13 and 14 for piecewise contours. And 15, 16 are path independence. And then orientation and reversal, 17 and 18. Lastly, you have challenging problems where you have 19 and 20. As usual, I'm going to solve two of these problems to drive home the point. So let's deal with that as we begin to bring this to a close. So I'm solving problems 11 and 19. So 11 and 19. So thankfully, we're taking one of the challenging ones. So problem 11 is evaluate integral 1 over z dz along gamma, where gamma of t is e raised power it, and t lies from 0 to 2 pi. And question 19 is a challenging one, which is to evaluate integral of x plus iy squared dz along gamma, where gamma of t is t plus it squared, and t is from 0 to 1. So let's go ahead and deal with these questions. So I start with problem 11. Problem 11. So the issue is to evaluate, or let me just write it the way I like to evaluate the integral of 1 over z dz along gamma. So where gamma of t is equal to e raised power it, and 0 is less than or equal to t is less than or equal to 2 pi, right? So that we want to do that. So for step 1, we parameterize. Step 1 is parameterization, which we have seen to be a key thing, parameterization, okay, which has been a very important thing here. So we take z, right, to be gamma of t, which is actually e raised power it, and that is equal to, and that implies that dz dt, of course, when we differentiate z with respect to t here, we get I e raised power it, so that uh dz itself is e I e raised power I e raised power it dt. So this is a very crucial thing here because we are going to need that for this expression. Then in that case, we can then simplify. So we try to simplify. So that is step 1, right? Then we move on to step 2. So step 2, we substitute, and the substitution we are doing is this. We have 1 over z, which is what we need to do here. So we have 1 over z, but we already know z, right? That is 1 over e raised power it, which is e raised power minus it already. So 1 over z is e raised power minus it. So we keep this very useful for the next stage. So The integral becomes, so the integral becomes integral from 0 to 2 pi. Don't forget that we have that 0 to 2 pi here already. So 0 to 2 pi. Um, then 1 over z is e raised to power minus it dot dz, which is I e raised to power it dt. Okay, and then that is equal to integral from 0 to 2 pi of e raised by this cancels this. I can come out and we just have dt left here. So the next thing is to just simplify. If you like, you can call that step 3. So in step 3 now, we try to simplify. Or is it integrate? I've simplified already, so we can just integrate. So integrate. So now we have that the integral of 1 over z dz is this over gamma is actually integral from 0 to 2 pi of I dt. So I is constant, so I comes out integral from 0 to 2 pi dt. If you integrate dt, you get t as usual. So this is t from 0 to 2 pi. So that means that we have I into 2 pi when you put 2 pi for t and 0. So that means you have I now equals, I into 2 pi minus 0, which is 2 pi. And all of that is 2 pi I. Okay? So you can then conclude that so integral over gamma of 1 over z dz is actually the same thing as 2 pi I. So what do we have to learn from this? So key insights from here now. Key insights. Key or is it key insight? Key insight. This result is fundamental. It is fundamental and shows that the integral along gamma of 1 over z dz is the same thing as 2 pi I for a positively oriented unit circle. For a positively oriented unit circle. Oriented unit circle. So that goes. So next we go for problem 19. Problem 19. So for problem 19 now, it's a bit more demanding. We need to evaluate integral along gamma of x plus iy squared dz. So where gamma of t is equal to t plus it squared, and 0 is less than or equal to t less than or equal to 1. So again, step 1. So step 1, we express components. So first of all, here, if you look at all this now, for component, it tells us that x is equal to t and y is equal to t squared. Because generally speaking, we want to have gamma of t is usually taken to be x plus I y of t. Okay, so if that is similar to t plus it squared, so it can only mean that x is t and y of t, sorry, x of t is t and y of t is t squared. Okay, so x is t and y is t squared. Basically, that's what we have there. And in that case now, we can say, so x plus iy squared is equal to x is t, I, then y is t squared, all this squared. So we have that. Then in step 2 now, step 2, we then expand. So to expand, we know that t plus it squared is what we have. So that means t squared plus 2 into t into it plus it all squared. So that means we have t squared plus I 2t squared, 2 times t times it plus I squared t squared. But I squared is minus 1, right? So we have t squared plus I 2t squared minus t squared. So this cancels out. So we know that t plus it all squared is equal to I 2t squared. like that, but that's not the destination. That's just a step on the way. So, oh, what have I done? Yeah, something is wrong. Yeah, yeah, something is definitely wrong. We have This is t plus it squared, not just t plus it. If it was just t plus it, then it would be that simple. But no, this is t plus it squared. So this is t plus it squared. So again, I go t squared plus 2 into t into it squared, right? Plus I squared t raised to power 4. Yeah? So t squared, 2 times t times it squared plus I squared t raised to power 4. Because this is t squared already. So this is t raised to power 4. So this is t squared plus I 2t raised to power 3 plus, minus, now minus t raised to power 4. Okay, so that's all we have there. So that's t squared plus I 2t cube, or if you like 2it cube minus t raised to power 4. That's settled. So the next thing we need to do is to compute dz. So step three now, compute dz. That's dz. Don't forget the problem. This is what we are trying to evaluate. So we have got this in terms of t. So we now need to get dz in terms of t. So we already have so to compute the z, we know z already is I because z is gamma of t. So z is t plus it squared. So dz, dt is actually 1 plus I 2t. So that means that dz alone is going to be 1 plus I 2t rather, dt. 1 plus I 2t or 2it dt. So so we can then move on to talk about the integral. So step 4 now, we form the integral. So again, don't forget, we have integral across this of x plus iy dz, x plus iy all squared, right? X plus iy all squared. Yeah, x plus iy all squared dz. So that is equal to integral now from 0 to 1. Why 0 to 1? We have, that is also given. T is from 0 to 1 here. So 0 to 1, right? Of course, x plus iy squared, we already found that to be t squared plus I 2t cubed minus t raised to power 4. So we have t squared plus I 2t cube minus t raised to power 4. Now, dz, we have also found dz to be 1 plus I 2t, 1 plus I 2t, 1 plus I 2t dt. So then we can multiply out, if you can call that step 5. So in step 5 now, we multiply out. So we need to do this expansion. So I think I'll just keep going. So integral along this of x plus iy all squared dz is now equal to integral from 0 to 1. So I'll just do my multiplying out like this. Um, so we have 1 times. Okay, we can do it in bits and pieces. So I want to collect all of that here as much as possible. Let's see how well we can do that. So t squared times 1, that's t squared. T squared times I 2t, that is plus I 2t cube. Then that's done. Then next we go for I 2t cube times 1. That I 2t cube. So I 2t cube times 1, that's I 2t cube. So I'm collecting like them straight. Then I 2t cube times I 2t. All right. I 2t cube times I 2t, that's like I squared 2t4. So I squared 2t4 means minus 2t4. You know, I squared is already minus 1. So I 2t cubed times I 2t. So I squared, that's minus 1. 2 times 2, 4. Oh, yeah, I think it's better I did that again. That's 4. I times I minus 1. 2 times 2, 4. T cubed times t, t4. good to know I didn't miss that. The minus t raised power 4. So minus t raised power 4 times 1, that's minus t raised power 4. I'm putting that together here. The minus t raised power 4 times I2t, that will be minus, that will be on its own. That'll be minus I 2t raised power 5 minus I 2t raised power 5. Okay, so that's the integral here from 0 to 1. Now, all of this now with respect to dt. So I just carry on. I have integral from 0 to 1. We can tidy things up now. So integral from 0 to 1 of t squared. Then this and this can add together. So we have, so that'll be plus I 4t cube. You know, that we have two of the same. That's I 4t cube. Then coming here, we have minus 5t raised power 4. Then lastly, I 2 I 2t raised power 5 dt. All of that dt. So that requires some carefulness. So t squared plus I 4t cube minus 5t raised power 4 minus I 2t raised power 5 dt. So then we can integrate term by term. Okay, so I think I'll just carry on. We integrate term by term now. So let me just carry this on. So this means integral over gamma of x plus iy all squared dz is equal to, so integrating term by term, t squared dt. If you integrate t squared dt, okay, this is what we mean. So we have integral from 0 to 1 of t squared dt plus, in fact, I'll move out the constants immediately. So I4 integral of t cube from 0 to 1 dt minus 5 integral t4 from 0 to 1 dt. I mean t4 rather. Yeah, that's it to 5. So minus I2 integral t5 dt like that. That we do that one after the other. So that's integral. So first one, we have t raised by 3 all over 3 from 0 to 1 plus I4 t raised by 4 all over 4 from 0 to 1 minus 5 t raised by 5 over 5 from 0 to 1 minus 2 I2, right? This is I2, not I squared. It's I2. Then t raised by 6, t raised by 6 over 6 from 0 to 1. Okay, so we are getting home gradually. So I like to bring out the constant. So 1 over 3 t cubed from 0 to 1 plus 1 over I4 multiplied by 1 over 4. If you bring out the fraction, you have t4 from 0 to 1 minus 5 times I5, into t raised by 5 from 0 to 1. Then minus I2 multiplied by 1 over 6, t raised by 6 from 0 to 1. So getting home, like I said, so 1 over 3 into, so I'll just substitute directly. So 1 cube minus 0 cube, then 4 cancels. So we have plus I into t raised by 4, that's 1 raised by 4 minus 0 raised by 4, settled. Then 5 cancels. So we just have t raised by 5, that's 1 raised by 5 minus 0 raised by 5. That goes. Then 2 here is 1, 2 here is 3. So we have I minus I over 3. So minus I over 3 minus I over 3 into 0 raised by 1 raised by 6 minus 0 raised by 6. Okay, so we have to be careful. So this is 1 over 3 into 1 because 1 cube is 1. So 1 and the other one is 0. So plus I into 1 again minus 1 minus I over 3 into 1. So we tidy up further. So that's 1 over 3 plus I minus 1 minus I over 3 like that. So we can collect like terms, right? So collecting the like terms, we have 1 over 3 minus 1 over 1. That's the ones without I. On the other hand, you have plus I minus I over 3. So you can say I over 1, I over 3. So this is equal to LCM is 3 here. 1 in 3 is 3. So 1 in 3, 3 in 3 is 1. 1 times 1, 1. 1 in 3, 3. 3 times 1, 3. Plus LCM here is 3. 1 in 3, 3. 3 times I, 3I. Minus 3 in 3, 1. 1 times I is I. So we have 1 minus 3, that's minus 2 over 3. 3I minus I, that is 2I over 3. So we have 2 minus 2 over 3 plus 2 over 3I. And that's what we get in that regard. So, um, so that's what we get like that. And that is how it all goes. So we can conclude. So integral along gamma of for x plus iy raised all squared dz is equal to minus 2 over 3 plus 2 over 3i. So that's how that goes. All right, so with this, we come to the end of this. Don't let me flash the problems again. Try your hands on this and let's see how well you get the gist. So this is here we have question. Okay, question 1 to 4 as usual, like I showed before. Then basic parameterization, then computing line integrals. We have all of that from 5 to 8, and then circular contours. We have 9 to 12. Then piecewise contours. Okay, we can fit piecewise contours and path independence together. That's 13 to 16. And then for the rest, you have 17 to 20. We're talking about orientation reversal and challenging problems. Let me know how helpful this is for you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed to this channel already, I thank you very much for doing that. And if you have not, what exactly would you say is the issue? So why not go ahead, subscribe, and hit the notification bell so you can always get alerted each time a new video is released. Having done that, you can also become a member of this channel by clicking on join. And joining gives you special privileges like seeing some videos first or being the only one to see some videos as a member of the channel. You can also request for PDF copies of my notes for your personal use. We could also hang out to discuss anything that interests you on my channel, be it mathematics, data analysis, data science, machine learning, writing books, scholarships, whatever. We can discuss all of that. We can hang out physically if you ever get to be in the same geographical location or online if we are not in the, I mean, if that is preferable. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.